had been disposing of the onion waste in the San Joaquin Valley for many years, trucking it over to San Joaquin Valley, and somebody brought to their attention they may want to digest that in a digester, produce a fuel, and operate fuel cells for power production, and that's what you see here. It says Gill's Onions right here, 600 kilowatts, two 300 kilowatt multi-carbonate fuel cells, producing electricity and then heat for the digester. Over 80% total efficiency, about 50% fuel to electrical conversion efficiency. Example number 3 is a demonstration, and I take you back to the wastewater treatment plant where we have a concept that's being evaluated, which is a strategy that in addition to the generation of electricity and heat, to generate also a fuel. And in this case, hydrogen for that fuel cell vehicle we talked about earlier. This would be biohydrogen, again coming from sewer waste, and this is almost the epitome of sustainability, meaning using our human waste to produce electricity, heat, and then a transportation fuel. We do call this tri-generation for those 3 products that are being produced. This is a one-off right now, but commercial applications are being submitted from around the world for this technology. It's located at the Orange County Sanitation District with a number of strategic partners. This is what it looks like behind the power plant, and this is what it looks like in front of the wall at the Orange County Sanitation District, where today, if you have a fuel cell vehicle, and about 200 do in Southern California, they can fuel up with biohydrogen. So that brings greenhouse gas reduction, not only from the high efficient fuel electrical conversion of the fuel cells, but here due to operation on a renewable fuel, a biofuel. Acoustically benign, virtually zero consumption of water, and a very nice fit for distributed generation. Just to drive that point home, again looking at our map, here's the distributed generation area. Here are the fuel cell attributes that work well for that. This high fuel to electrical conversion efficiency, high quality heat for combined cooling, heat, and power. Acoustically benign, since it's around people, you wish to have that attribute. And of course, also because it's around people, the virtually zero emission of criteria pollutants. But there's another attribute that I want to add to this that you will want to see coming in the future. It's right about here. It's called a fuel cell gas turbine hybrid, where we actually marry a gas turbine with a fuel cell, remove the Carnot efficiency constraint of the gas turbine, and make it much more flexible to reach efficiencies that we never thought we could imagine, let alone achieve in the future. What that is shown here diagrammatically, where a gas turbine comes in and marries with a fuel cell. You would like to do this where you don't have a capacity to utilize the heat, or where you want to have a more simple system just producing electricity. The other application of this that's well underway is out in central power generation. Fuel cell gas turbine hybrids, because of their very high efficiency and other attributes. In fact, if I can take this a step further, you see this technology starting to arrive, but you have to be looking for other applications, from long distance trucks to ships, and in this case, to repowering locomotives. Here you would have a locomotive with over 70% efficiency, zero emission of criteria pollutants, and acoustically benign attributes that we're looking for in that. But now I've gotten a little bit off cue, and David has reminded me that we have to bring this home. So let's bring it home with this slide and come back to our grid and just look at where we're at. We have the grid now with fuel cells populating the grid. We have the challenge, as David alluded to, of how we're going to handle the intermittency associated with renewable power generation. We have a population that David also alluded to with these plug-in electric vehicles that are creating an interesting perturbation and also a potential asset to the grid. This is giving rise to the consideration of technologies, as you've heard about in the conference, of electrical storage in the distribution system, of electrical storage out here in the transmission system, and even now we're demonstrating electrical storage in the residential and community areas as well. Finally, we've talked about fueling of vehicles. This is a gasoline station. What we're doing in the country is, and around the world, is to take an island of gasoline and replace it with hydrogen in order to provide that asset for the fuel cell vehicle future. One of our goals, as we pointed out, is to capture some of that hydrogen from a wastewater treatment plant. You can imagine piping it from the wastewater treatment plants to the point of use, as I show here. And if you've been following this energy economy with hydrogen, you also know that we have a fine opportunity over here of generating hydrogen renewably through electrolysis, providing hydrogen storage and a hydrogen carrier, and piping that back. But you may not know, as in these advanced hybrid systems, we're looking at the cogeneration of not electricity, but of a fuel as well, where the hydrogen can come back and provide that fuel for the urban sector. In the electrolysis, I just brought up here a curtailment, which is a way of utilizing that energy that would otherwise be abandoned, and then, of course, using pipeline instead of transmission lines to address the challenges that we're facing with additional transmission line deployment. Let me conclude with that and respond to any questions you might have. Thank you.
Thank you, Scott. And that demonstrates, I think, very interesting transition technology. So we will now have 7 minutes for questions from the floor and answers. Over to the floor. Yes, Jim.
In reforming natural gas to make hydrogen, a carbon atom or hydrogen atoms, what happens to that carbon atom?
Question is, what happens to the carbon atom when one reforms the methane or natural gas into hydrogen? That carbon atom is emitted into the atmosphere, so it's carbon dioxide. And you'll notice on here, I said no tank emissions of CO2 or no automobile emissions of CO2. And you're correct to bring up that we have a challenge of assuring that in the production of the hydrogen, we also minimize, if not preclude, the emission of carbon. So the bio application you saw here, the electrolysis, would be means of doing that. But right now, we are dependent upon the majority of the hydrogen coming from steam methane reformation. On the other hand, let me conclude by saying that in many of our countries throughout the world, we're using hydrogen to produce gasoline. So we're actually not going to be using more natural gas. We'll be displacing natural gas currently used to produce gasoline from steam methane reformation with hydrogen. But nonetheless, your point is very much on target.
Frank, would you like to use the microphone?
Yes, I run a gas distribution company. I had about 4 of the 200 kV units. I'm not going to mention the manufacturer in the 90s, but the reliability just wasn't there, and I think it had to do with the reformers, the fuel reformers. Has it improved since the mid-90s? Because it was nowhere near what the grid was able to offer.
Yes, and so the question is, has the reliability of fuel cell technology improved in the last 2 decades? Yes, it has. The commercial market would not be so productive if it had not evolved to this point. Electricity to us, all of us in this room, is very much like flying on an aircraft. We want those engines on the aircraft to be reliable, and we want this electricity to be reliable. So for fuel cells to be successful in this market, they had to prove their reliability. Much of that occurred during the 1990s, but usually most of it occurred during the first decade of this millennium, over the last 8 to 10 years. And there's still improvement occurring, but the product is today where it's now approaching 94, 96 availability and showing that it is a viable option, if not the go-to strategy for the electrical market in the future. On the automobile, the evolution has been even more dramatic and faster really over the last 5 years, probably due to the competition between the automobile manufacturers and their recognition that this is their future. So to be competitive in the future, they have to be successful with this vehicle. And it's not only making a reliable vehicle, but it's got to be turned on and off, on and off, on and off over at least a 10-year period. And then in areas such as Minnesota and Anchorage and Fairbanks especially, It has to demonstrate cold weather operation. Platinum has to be reduced, and all of that has occurred under the hood of the automobile. So I'm pleased to say, yes, reliability has occurred dramatically in both the stationary and the mobile application.
We'll take one more question.
Thanks. All very fascinating. It sounded though like there was a lack of numbers in terms of what all this costs. So you gave us a nice technology overview, but absolutely no basis on which to assess whether this was a good idea.
I'm not sure why that would be of interest to you. You're economists after all, absolutely. So I kind of teased out that question. Thank you for responding. So the cost is a factor, of course. Historically, fuel cells have been quite a bit more expensive than the competition. The competition would be a gas turbine, and generally we refer to $1,000 per kilowatt installed as being the mark that we need to reach for fuel cell technology. Last year, we were about 3 times above that at $3,000 per kilowatt. We're starting to solidify that. And the price is coming down due to the additional mass production, not so much anymore due to the technology improvement. That Korea market that I showed you was very powerful in getting the mass production up for fuel cell energy. And then the success of Bloom Energy in not only the California market, but now in the East Coast, they're starting manufacturing in Delaware, will bring down their price as well. In California, as an example of incentive, they're still benefiting from what's called a self-generation incentive program that underwrites about half the cost of the fuel cell. But right now, we're projecting that within 3 years, the fuel cell cost will be a bit below $2,000. And you might say, well, it's not quite at the gas turbine, but the fuel cell attributes of this acoustically benign, no pollutant emission, and this very high efficiency, really twice that of a combustion engine, means that the operating costs will be dramatically less, so the overall lifetime getting into an economic analysis will be very, very attractive, and is today, albeit with an incentive from the state. Thank you for your questions, and look forward at the end for additional questions as we have time. Thank you.
I'm afraid we have to stop there. We can catch Scott afterwards and ask other questions. And now I'd like to call out Mira to talk about the AVIC.
Good morning. I'm afraid I'm going to be a far less technical presentation. Okay, so what I'm going to tell you about is our real-world situation here in Alaska and what we do every day to try and provide reliable power to very, very small communities across the state. So I'm going to tell you a little bit about Alaska Village Electric Cooperative. We are a nonprofit electric utility. We are based here in Anchorage, and we serve 55 villages that are scattered across the state. If you rolled all our villages together in one place, we would have a population close to 23,000 people, which would make us the 4th largest community in Alaska. So we're not exactly very heavily populated in the state. Our smallest village is well under 100 at 69, and our largest village is just over 1,000. So as you can see, the average works out to about 415 people in one location, and you can compare that with Anchorage, which is about 300,000 people right now. So here in Anchorage, we have half a dozen power plants that serve the city. We actually own 48 power plants to serve our 55 villages. So that is a huge capital investment that we wind up inevitably with. We have been working on interconnecting our villages because we believe that's how we're going to achieve better efficiencies, better reliability, and all the wonderful attributes that Scott talked about as time wears on. The way that we operate is that we actually have diesel fuel-fired generators. That really is the only option because in these locations, there isn't a local source of any energy because the demand is so small that it doesn't justify the development expense that it would take to build a renewable energy or alternative energy source. We do, however, have the largest wind turbine fleet in the state, at least today, 34 wind turbines. They are typically just 100 kilowatts in size, but that's because the average load in a village is about 100 kilowatts, and so very much more than that becomes a real challenge. We actually have interconnected a few villages where with the combined load, we now have 400 kilowatts of generation in a couple of locations, and so we're actually able to achieve about an 85% penetration at the peak production levels. So we demonstrate a very high level of penetration. However, overall our capacity factors are relatively modest. We also did something innovative a couple of years ago when we built 2 sets of tugs and barges to deliver our own fuel to the villages, because the delivery of fuel in this state comprises a very large portion of the cost of the fuel to the engine. And by taking control over that, we sort of manage our own destiny. Here is what we look like. I'm sure many of you have seen something like this, where we superimpose the state of Alaska on the United States to show you that we encompass 20% of the land mass of the United States. And the purpose of this is to show you the distances that we deal with. This is our northernmost village, Kivalina, that's well above the Arctic Circle in the Northwest Arctic Borough. This is our southernmost village over here on the island of Kodiak. That's Old Harbor, and it's about 824 miles north to south. This is our farthest west village, Gamble, which is on an island out in the Bering Sea. And then we have our farthest east village, which is actually on the road system. We have one village that's on the road system. Arguably it is a 70-mile George Road, but nonetheless it is a road. So it's more than 600 miles east to west. So if you multiply those two, we serve an area of essentially about 500,000 square miles. So we are based right here in Anchorage, and our technicians, we have about 35 employees who travel full-time. Those are our linemen and our power plant our power plant technicians, mechanics, and so forth. And they fly out to all of these villages. Typically, it's 2 plane rides. You can take a jet, for the most part, to a hub like Fairbanks or Bethel or Nome or Kotzebue, and then a small plane from that point on to the village. One of the challenges we have in the state is that we have no roads and we have no transmission system. There is no grid. So this is almost the entire amount of the interconnected road, and this portion here is the haul road. It's a gravel road that goes from Fairbanks up to Prudhoe Bay. And I'm sure many of you may have seen episodes of Ice Road Truckers and other reality shows. They're all based upon the challenges of life in the last frontier, which is what we call ourselves. So the grid that we have right now is basically from Fairbanks down to Anchorage, and then on to Seward and Homer. So that's it. That's all the grid that we have. All the rest of these communities in the state have to have their own isolated distribution grids. When we connect our villages, we call them InterTies. We don't call them transmission grids because they're operated at standard distribution voltages. So they're basically 25 kV or 12.5. Here's what our power costs. Our retail rate, the average retail rate for our system statewide is almost 58 cents a kilowatt hour. Many of you are not involved with the electrical industry, so you look at your bill, and your electric bill occurs to you in the form of a dollar amount. So it's $60 a month, or it's $100 a month, or something like that. Very few people know how much a kilowatt hour costs. Here in Anchorage, it's about 13 cents a kilowatt hour. Out in the villages, it's about 60 cents a kilowatt hour. And electricity is only a fraction of the energy that's used in the home or in the business. Typically about 25% of the energy that's used. The rest is for heat. And so it is not uncommon to have a rural family that spends 50% or more of their disposable income in a year on home energy. So it's a real challenge in our state. Transportation is a huge issue. Obviously, we have no roads, and the rivers are frozen for most of the year, so we have a very short shipping season when barges ply the waters of the rivers, and it typically lasts 4 to 5 months. So as we're putting up wind turbines, we use the barges, and there's no local equipment to move heavy objects around. So you can see over here we have a 12,000-pound nacelle for a 100 kilowatt wind turbine, and here's the local forklift that right now is losing the battle to get that thing off the barge. And here's how we move. You have to be creative. You create your own little dolly over here and use whatever you have in the community. But you can see the condition of the roads. There are no asphalt roads or paved roads anywhere in rural Alaska. They're all dirt roads. And because we have permafrost, what happens is that the permafrost thaws only down to 3 or 4 feet below the surface, so you have this boggy mass that you have to deal with at all times. Another challenge, obviously, is moving our electrical equipment from village to village, and here you see we have a lineman that's moving equipment between 2 villages. You've got the wire here, you've got the hardware here, you've got the transformer here, you've got the service wire here, and there's the pole. We have our issues and our challenges, but we have been interconnecting villages. These names will probably mean very little to you, but these are existing InterTies between our villages. So we have essentially 8 villages that are connected to other villages, and so don't have generation in their own community. We are currently actively building additional InterTies across the state. And there are many pluses and minuses to building InterTies. First of all, when you close down a power plant, you reduce the noise, the pollution, the cost of operating a power plant. Our experience has been that the cost of operations and maintenance of InterTies is actually quite low, lower than conventional transmission system. We get higher efficiencies, we get more renewable interaction when we have additional load. And the capital cost of building an InterTie is typically significantly lower than that of building a standalone power plant and tank farm. Obviously, we're challenged by construction issues. We're challenged by the fact that there are very few permanent jobs in communities. These are very small communities with no industrial activity, very little commercial activity. And so as a result, every job is precious. And so we wind up with having to juggle some job issues. And then a big one, Scott talked about recovered heat out of fuel cells, recovered heat out of internal combustion. Diesel engines is also very critical. It's used typically for, not necessarily for district heat, but for local heat for communal washaterias, water treatment plants, schools, and city buildings, essentially. So what we have been working towards in the last couple of years is building what we call microgrids. The intent would be to interconnect those microgrids and make them into mini-grids. Interconnect the mini-grids, make sub-regional grids, interconnect those, get regional grids, and pretty soon you actually have a grid. It's a real challenge here in Alaska because if you take the entire electric sales, retail electric sales from utilities in the whole state, which as you can see is a very large beast, the total is 6.5 billion kilowatt hours. That's a little less than half of what is sold in Sacramento. Sacramento really doesn't have a lot of industry. We have